third year students of analytical chemistry. Here we are going to learn about the H1 NMR spectroscopy. In last lecture we have learned about the theory of H1 NMR spectroscopy, what type of requirement is there for the H1 NMR. Then H1 means what? Proton nuclear magnetic resonance spectroscopy. Today, friends, we are going to learn about the topic, that is what? The instrumentation and techniques of the H1 NMR. So let's begin with the instrumentation and techniques of the H1 NMR spectroscopy. So uh, for the instrumentation for the NMR spectrometer, the schematic diagram for the important components of an NMR spectrometer is shown in this figure. What happening here? What RF generator is there? Magnetic sweep generator is there. Here what magnet is there? Pole magnet is there, and this sample tube is there here, and a receiver's coil is there, and this uh, RF rectifier or detector, and here recorder is there. So whole is the what? The instrument for the NMR's H1 NMR. Then see, we'll see in detail one by one part of the instrument. So the magnet, first important part is the what? Magnet is there. Then friends, what type of magnet is there? High power magnet is required for the what the NMR active species to be what bring in the resonance. So the sensitivity and resolution of an NMR spectrometer are what critically depend upon the strength and the quality of the its magnet, because all the what working of this instrument is depend upon its magnet. So both sensitivity and the resolution, sensitivity as well as the resolution increases with increase in the field strength. What? H0, that is what is the field strength? It is what the whatever the field strength, it increases the sensitivity, and resolution of the spectrum also increases. In addition, however, the field must be highly homogeneous and reproducible. What? Homogeneity is the very important during the what? Measurement of the NMR or the analysis of the NMR, because the field is the homogeneous all in the all direction. Field is what? The homogeneous and reproducible. These requirements make the magnet by that is for the most expensive component of the NMR spectrometer. So the most expensive and important component of the NMR spectrometer is the magnet, due to the its field strength, homogeneity of this field strength. So spectrometric magnets are of the three types. The magnet used in the NMR spectrometer are of three types. So uh, permanent magnet, conventional electromagnet, and superconducting solenoids. These three types of magnets are required for the spectroscopic measurement. The permanent magnets with the field strength of what the 7046 gauge or 14,092 gauge are used in the several commercial instruments. So commercial instrument contains a permanent magnet with field strength, that is what the 7046 gauge and 14,092 gauge are used. So a corresponding oscillator frequencies for the proton studies are 30 and 60 megahertz. So for the proton NMR, the oscillator used are 30 and 60 megahertz capacities. So permanent magnets are highly temperature sensitive and require extensive thermostating and shielding. So these are the temperature sensitive, so it is required to thermosetting and the shielding for the what the uh, that permanent magnet. So electromagnets are the relatively insensitive to the temperature. So electromagnets are not sensitive to temperature, so no, not need to thermosetting and what shielding. So fluctuation but requires a cooling systems to remove the heat generated by the large currents that are the required. So what is the requirement for the electromagnet? It required the coolant, that is what the cooling, due to what remove heat produced due to the large current. So uh, elaborate power supplies are also necessary to provide the required stability. So if you name suggests itself, electromagnets means magnets generated by passing electricity. So power supply is also, elaborated power supply is required for the stability of the electromagnet. Commercial electromagnets generates field about what the 14,092 gauges or 21,138 gauges, as well as the 23,490 gauges. So corresponding to the proton absorption frequencies, that is RF frequencies, what is 60 to 90 and 100 megahertz, corresponding to all these field strength, that is what the 14,092 gauges, 21,138 gauges, as well as 23,490 gauges, corresponding to proton absorption frequencies is about 60 for 14,092 gauges, 90 hertz for 21,138 gauges, and 100 megahertz for the field strength 23,490 gauges. So this is the requirement. Superconducting magnets are used in the highest resolution and most expensive instruments. Here, field as the great as 110, sorry, 1,10,390 gauges are attained, corresponding to the proton frequencies of 470 megahertz. So such type of the huge field strength is provided by means of the superconducting material and this superconducting magnet. These superconducting magnets are used in the highly sensitive instrument. It is the very expensive one, and the performance specification for the spectrometer magnet are stagnant, means what the important. So the field produced must be homogeneous to a few parts per billion within the sample area, and must be stable to a similar degree during the spectrum recording time. Unfortunately, the inherent stability of the most of the magnet. So what is the requirement is there during the what the recording the spectrum? We require the few parts per billion uh, gauges folds. What the field strength is the homogeneous all over the instrument, and during the what it is stable during the what spectrum recording. So a magnet is the considerably lower than these variations. A large as one part is 10 to the 7 are often observed over a period of 1 hour. So what is the homogeneity? It is what you are 1 hour. It is 10 to the power 7 is used, is oftenly observed. In order to offset the effect of the field strength, that is field fluctuation, a frequency lock system is employed in all commercial NMR instrument. Here a reference nucleus is continuously irradiated and monitored at a frequency corresponding to its response resonance maximum at the related field strength of the magnet. So what is the alternative method used in the instrument is that the reference uh, in the reference cell, the sample is what continuously irradiated with the stable frequency and monitored at the related field strength of the magnet. So changes in the intensity of the reference absorption signal results from the drifts in the magnetic field. The control the feedback circuit, the output of which is fed into the coil into the magnetic gap in such a way as to the correct for the drift. So what is the fluctuation? Fluctuation is removed by means of using the reference sample by irradiating this with constant field, and this drift is fed to the coil, and what is the gap in the fluctuation in the magnetic field is maintained by means of using references. So two types of the lock system, that is what the frequency lock systems are encountered. The external lock employed as a separate sample container for the reference substances, and this container must be locked as close as possible to the analyte container. So what is the frequency lock is used, that is for the reference compound, and it is nearly equal to the what the analyte container. So in the internal lock system, the reference substance is dissolved in the solution containing the sample. So in the what the external systems is there, the two, that is reference and the samples analyte are the closer, and in the internal system, here what the reference solution, reference substance is dissolved in the solution containing the samples. So it is what the internal. The reference compound is usually tetramethylsilane, that is tetramethylsilane, which also serves as the internal standard. So it is used as the internal standard. It shows the delta value at 0. The external lock system provides control of the order of parts in 10 to the power 9, while the internal lock system gives the control of the order of the part 10 to the power 10. So this is the difference between internal and the external lock system. Second part is the magnetic sweep generator. A pair of coils located parallel to the magnet faces permits the the alteration of the applied field over a small range. So what this magnetic sweep generator is used for the what? So such type of coil you have seen in the instrument. See, parallel coils are there, magnetic sweep generators. So such type of the coil is used to, sweep coils are used to what is the use of this sweep generator, magnetic sweep generator? So two types of the locks are there. See, the internal, external. Then the magnetic sweep generator. A pair of coils located parallel to the magnetic faces permits alteration of the applied field over a small range. So alteration of applied field is done with the help of the two pair of the coils, parallel coils or magnet faces. By the varying a direct current through these coils, the effective field can be changed by the few hundred milligauges without loss of field homogeneity. So for the maintaining field homogeneity, this magnetic sweep generators are used because they what produces few hundreds of the hundred gauges of the field strength by without changing the homogeneity by using the by varying the direct current. So the radio frequency generator, the signal from a radio frequency oscillator transmitter is fed into a pair of coils mounted at 90 degree to the path of the field. The output of the radio frequency through these coils is plane polarized. A fixed oscillator strength of the exactly 60, 90 or 100 MHz frequency is ordinarily employed, corresponding to the magnets used of the magnetic field strength of about 14,092 gauges as well as 21,138 gauges or what 23,490 gauges. So depending upon there, these what the pair of coils mounted at 90 degree to the path of the field is fed to that the signal from the radio frequency oscillator is fed to into a pair of coils mounted at 90 degree to the path of the field. The output of the radio frequency through their coils is plane polarized. You will get the plane polarized output. A fixed oscillator strength of the exactly 60, 90 and 100 megahertz frequency is ordinarily employed, corresponding to the magnet used for magnetic field strength is about what 14,092 gauges, as well as what 21,138 gauges, or 23,490 gauges. So for high resolution work, the frequency must be constant to about 1 part into 10 to the power 9. The power output of this source is less than 1 watt and should be constant to perhaps 1% over the period of running the spectrum. So, what is the use of this? What the use of that radio frequency generator is to what get the resolved spectra, resolved spectrum. So, the radio frequency signal detector and recorder system. The radio frequency signal produced by the what the resonating nuclei is detected by means of the coil that surrounds the sample and is the radio frequency signal produced by the resonance nuclei is detected by the means of a coil that surrounds the sample and is mm, at right angles to the source coil and the magnetic field. Thus, the electrical signal is generated by the radio frequency receiver coils. Thus, the electrical signals is very small and therefore amplified by the factor 10 to the 100, that is 10 to the power 5 or more, and then fed to the recorder. So, what happened here? What the see here? What the this coil, what the RF generator feeds the signal to the coil, and these signals are fed to the receiver, and this receiver what records the signal on the recorder. So this is about the use of the radio frequency signal detector and recorder system. Then the abscissa derived of the an NMR recorder is the synchronized with the magnetic field sweep. Impact recorder controls the magnetic field sweep rate. The response of the recorder to the electrical signals must be rapid, and it is also desirable that the sweep rate can be what the uh, sweep rate can be varied. So all modern NMR recorder are equipped with the electronic integrators to provide information regarding area under the absorption peak. So with the help of recorder, with the abscissa, we can record the spectrum with what the varying frequency as well as the varying that is what the abscissa derive an NMR according that is the recorder is synchronized with the magnet field sweep. In fact, the recorder what controls the magnetic field sweep rate. So magnetic field sweep rate is what controlled by means of the recorder. The response of the recorder to the electrical signal must be rapid. It gets a rapid response, and it is also desirable that the sweep rate can be what the varied. So all the modern NMR recorder are equipped with the electronic integrators to provide information regarding the area under the absorption peak. So what is the use of this? It provides the area under the absorption peak. The sample holder and sample probe. Most important is that what type of the sample used for the NMR recording, and how the sample holder is there. The usual NMR sample cell consists of 5 millimeter outer diameter glass tube. The 5 millimeter outer diameter glass tube containing about 0.4 ml of liquid. Microtubes for the smaller sample volumes are also available. The sample probe is a device for holding the sample tube in a fixed spot in the field. So the in the field required good sample probe. So the probe contains not only the sample holder but the magnetic sweep coils, RF generator coils, and the RF detector coils, as well as the assure reproducibility positioning. All are there of the what the sample with respect these components. It may also contain the reference cell as the external lock and the internal lock is there. The source and the receiver coils are oriented at the right angles to the another to eliminate the transfer of radio frequency radiation in the absence of sample. So the sample probe is also provided with an air driven turbine for rotating the sample tube at the several hundred rpm, that is what the revolution per minute, along its longitudinal axis. The rotation serves to average out the effects of the inhomogeneities in the field. So sharper lines and better resolution in the then obtained. So this is about the instrumentation. Then experimental technique. What type of the experimental technique is used for NMR spectroscopy? The sample must be in a non-viscous liquid state, not in the viscous state. So most commonly solutions of the sample, that is 2 to 15%, are employed. So what is the concentration? Is 2 to 15% are employed. If this sample is pure non-viscous liquid, it can be used as it is. If solutions that is what the sample is not viscous, then it is liquid, then it is used as it is. For solids, the best solvent for the H1 NMR spectroscopy contain no proton. From this standard point, CCl4, CS2 are ideal. If you use if you are using the solvent for the preparation of solution, then use the solvent without proton. That means the solvent does not contain protons, such as the chloroform, that is CCl4, CS2, carbon disulfide is the ideal one. But due to the low solubility of the many components in these solvents, a variety of deuterated solvents are used. Deuterated, that is what the chloroform is there, CdCl3, and deuterated benzene, CDC C6D6, or deuterated dimethyl sulfoxide, that is DMSO, deuterated DMSO, CD thrice twice SO can be used. So this type of the solvents used due to the insolubility of the sample. The solution of the sample is taken in the sample tube, to which a trace of reference substances is added, which also serves as an internal lock for the field fluctuations. The sample is placed in its position in the sample probe. The sample probe also holds the magnetic sweep coils, RF source, that is source, and detector coils. All these are wounded over the sample at the fixed position at right angles to the each other, as well as the 90 angles to the uh, sample holder. The sample probe is then inserted inside the NMR instrument. Strong magnetic field of the order of about what the 14,092 gauges and 21,138 gauges, or 23,490 gauges, 90 gauges is applied, corresponding to the radio frequency oscillator strength is about 60, 90 and 100 megahertz respectively, depending upon their field strength. The measurement of RF absorption signals, as the excess of absorbing nuclei in the lower energy states are very small. It is seldom possible to measure the change in the power of RF radiation. After absorption by these nuclei, therefore, nearly all NMR instruments employ an arrangement by which the magnetic uh, magnitude of a positive absorption related signals is determined, the logic of which is the desirable what they describe below. What happen when very small amount of the nuclei come in the resonance and that are measured by means of the uh, that is NMR. So, as the excess of absorbing nuclei in the lower energy states are very small, so it is seldom possible to measure the change in the power of RF radiation, radio frequency radiation, after the absorption by these nuclei. Therefore, nearly all NMR instruments employ an arrangement by which the magnitude of the positive absorption related signals is determined. Only positive absorption signals are determined, and the logic of which is described. So what following figure shows the schematic alignment of the major components of the NMR spectrometer on the Cartesian coordinates. How this sample orients with respect to the coil. See here what given, how this radio frequency source generator coils here, and here at perpendicular level radio frequency receiver coils are there, and here what the radiation plane polarized xz plane is there, and here is the what direction of magnetic field. So no signal in y direction is there, so only signal in x direction. So the x and z direction. So the radiation source is in the coil, that is a part of radio frequency oscillator circuit. So radio frequency radiation forms such a coil are plane polarized in the xz plane, not in the y plane. So the detector is a second coil located at right angles to the source on the y axis. So and is a part of the radio frequency receiver circuit. So the magnetic field used in the NMR experiment has a direction along z axis perpendicular with respect to the both of the source and the detector also. The plane polarized radiation can be resolved into two circularly polarized component that rotate in opposite direction. So plane polarized radiation can be what resolved into the circularly polarized component, so rotate in opposite direction to the one another in a xy plane. So therefore there is no net component of this plane polarized radiation along the y axis, so thus the no signal is received by the detector located at that axis. So there is no signal from the y-axis. The absorption signal here, reference detector, and what the this is x. The plane polarized RF radiation here, not the signal is generated. So if now a sample is placed at the origin of the 3 axis, and if their RF source has the frequency that is absorbed by the particular type of the nucleus in the sample, a power of one of the two circular components of the plane polarized beam is diminished, and the emerging beam of the radiation now has the fluctuating component in y direction. See here, we will get the RF direct detector, so we will get the signal at that time in the y direction. But in first step, if you keep the source at the z and xz plane only, not origin, then you will not get the signal what on the y axis. So we'll get the absorption signal. If you place at the origin sample or source at the origin, then we'll get the signal along the y axis, so y direction. So which is cause the detector to response, and thus sample serves to couple the RF generator to RF receiver. So provide the frequency of radiation corresponds to the resonance frequency of the nuclei in the magnetic field. So we'll get the uh, signal in the y direction due to what the coupling of the receiver coil and generator, so source coil. So uh, the strength of this positive absorption related signal depend upon the number of absorbing nuclei. So positive absorption signal will get depending upon the absorbing nuclei, and what is the condition for that is nu is equal to 2 mu beta and h0 divided by, that is 4. So the radio frequency absorbed by the resonating proton is proportional to the applied magnetic field. So new frequency is directly proportional to the applied magnetic field. So just by keeping RF constant and by varying the applied magnetic field by sweep coil, different protons of varying chemical environments can be brought into the resonance. So for the bringing this or the proton into the resonance, we will require to what mm, we require to change the field strength, and when varying the field strength we what bring this nuclear all nuclear in the resonance. One next one is the representation of NMR spectra. In NMR, it is what the absorption of the radio frequency radiation which is detected as the field H0 is increased, so that the precisional frequency means what the top rotating frequency, top like rotating frequency, precisional frequency of the proton increases, and when this frequency becomes equal to the frequency of oscillating RF field, resonance is developed. When resonance is developed, when the precisional frequency of the proton, that is around movement of the proton, that is frequency of precisional frequency is equal to the what the RF frequency, and then this condition occurs when a resonance is what developed, which causes the absorption of radio frequency by the proton and reveals by the spin of the proton. So due to the spin of the proton, the radio frequency absorbed in this process produces a signal which is detected by the RF detector. So whatever the signal after absorption is what form, such signal is detected by the detector and RF detector, which is converted to electrical signal and which is then amplified and recorded as the absorption band in the spectrum. So two methods are employed for the producing NMR spectra. One method is analogous to the optical spectra, and it involves the measuring of the absorption signal as the radio frequency is varied, and but the radio frequency no dispersing devices such as the prism or grating exist. For such change of RF, variable RF oscillator with the linear sweep is required, which changes the RF continuously over a range of 1 kilohertz for proton. The plot what between absorption signal and various RF will be of the type. So what happened, there are two types of the techniques used. One is the optical method in this, but in this optical method only we are what dealing with the change in the frequency, that is RF frequency, and by changing the frequency, a variable frequency of oscillator without any optical instrument, that is what the any slit or any what the grating or prism, we are what recording the optical means. And so by varying the only RF oscillator frequency and by sweeping it and about what is the rate of this is 1 kilohertz, and the plot between the absorption signal and various RF will be of the type. See, such type of the plot will get at the different proton, that is here one peak, here three peak, here uh, another type of the peak is there. Absorption versus frequency RF radiation is what the uh, taken, and what this an alternative way of the collecting our spectrum is to be employed constant RF frequency radio oscillator and SIP the magnetic field H0 continuously, since for the given nucleus frequency and field strength are directly proportional as per the equation nu is equal to 2 mu beta h uh, into h0, that is mu is directly proportional to the field strength. So we are changing field strength, we are changing frequency, so resonance is occur, and RF is what get absorbed in frequency, and this absorbed RF is what recorded as the absorption spectra and the signal. So H0 can be served equally well as the abscissa for an absorption spectrum. This method is called as magnetic sweep method, which is what represented below. So absorption H0, with the help of this we will get the clear spectrum, and the magnetic field sweep method is more accurate and easy than the linear RF sweep method. So this is about the uh, instrument techniques used for the NMR spectroscopy. If you have any queries regarding this topic, please ask the question in YouTube comment box. Thank you. Thanks a lot. Have a nice day.